So if you recall, last time I talked about many completion stage methods. So we talked about some completion stage methods that run after the completion of a previous stage. So things like then apply, then accept, then compose. And then we talked about some completion stage methods that complete after both previous stages complete. So things like then combine. And we also talked about completion stage methods that are applied after either of a previous two stages complete. And that would be things like accept either. And knowing about those things, some of those things will make your programming assignment much easier to do because it builds on that stuff. What we're going to do today is we're going to illustrate how to apply these things to a program, which you can find here in the example 8 directory. And this is used to do various types of asynchronous computations on big fractions. And it's a good file to look at because it shows off pretty much all the methods you need to know. And then I'll also talk here about how to handle runtime exceptions, which are kind of interesting in the context of completable futures. So by the time we're done, we will have covered all these things. We will have talked, of course, about the basic methods, right? Basic methods would be get and join and complete and is done, is canceled, all the simple things that come from Java Future that we said was kind of lame. The factory methods, which are used to initiate the asynchronous operations, so supply async, run async. The completion stage methods, of which there are many, we just talked about those. The exception methods, which we're about to talk about, and then the so-called arbitrary arity methods. So that'll give you an idea of all this stuff. Okay, so here's the example that this file has lots and lots of methods in it. I'm just going to focus on one of them called test fraction multiplications. And so it uses completable futures and streams and a bunch of cool things. So here's how it starts out. We're going to make ourselves a function lambda, right? What the heck is a function lambda? A function lambda basically says, here's a parameter to be passed of type big fraction, and here's the result that's going to come back from this function. And then we define a lambda expression that will basically be passed a fraction, which in this case is an unreduced fraction. And then we're going to go ahead and do some stuff to it. So this is a lambda. We're going to define a lambda called reduce and multiply fraction that's going to reduce and multiply a big fraction. So that's not too hard. And of course, that fraction will be unreduced. So what we're going to do is we're going to asynchronously run in the background a method that will reduce an unreduced fraction. So an unreduced fraction is just a fraction that has not been turned into a reduced form, right? It's going to have some big denominator and some big numerator, and they haven't been reduced to their simplest form yet. So that's going to run asynchronously in the background somewhere. And then when we're done with that computation, we're going to go ahead and multiply the reduced fraction by some other big fraction. So, reduction could take a while if you have a big enough numerator and denominator, and multiplication could take a while if you have a big enough numerator and denominator, right? So these are both things that will take a while to run. So in both cases, we're going to run them asynchronously. And as we talked about before, supply async is going to return it's going to return a completable future, and we want this thing to be able to then, compose this stuff together so we end up with a result which is a completable future to a big fraction. So that's what we're going to get when we're done with this. So that asynchronously multiplies the big fraction. Okay, so keep this method in mind, what this thing is trying to do. We're then going to define another lambda. This is a consumer lambda this time, and this is going to sort and print a list of reduced fractions. And this has got this really cool, clever approach for doing multiple sorts and seeing which one finishes first. So what it's going to do is it's going to take the list. So we have a list that's an unsorted list, and we're going to apply quicksort to quicksort it in the background asynchronously, and we're going to asynchronously merge sort it in the background, right? So both these things are going to go off and run in parallel. And then we're going to accept which either one of them finishes first, right? So If quicksort future finishes first, then we're going to take the result and use that. If merge sort finishes first, we're going to take the result and do that. So this is basically, these things that are coming back here will be the lists of big fractions that we're then going to go ahead and handle. And notice how we do this. Yeah, I'll get you one second. What we'll do here is we get back results. Results is a list. And so for each element in the list, we're going to display the mixed version of the fraction that's in that list. I'm sorry, go ahead. Great question. It does not cancel the other one. I should have put a little comment down here that said that. Yeah, that's a little weird. So it doesn't actually cancel it. It would be nice, honestly, if it did cancel it. But you've got lots of cores, so hey, what's the heck? It wasn't busy doing anything anyway, so let's just go ahead and use it, in an embarrassingly parallel way. Okay, so these are two things that we want to know about, right? So we want to be able to do reduce and multiply fraction. That's a lambda function, and we have the print sorted list consumer lambda, and then down here we're going to put it all together, right? So this actually illustrates a bunch of interesting things. So make big fraction is a factoring method that will go ahead and generate a random big fraction, where it has a random big numerator and a random big denominator that's been unreduced. That's what false means here. And this is a very interesting method. This method is marginally interesting. This is what the interesting method is, generate. So what generate does is generate will create an infinite stream. So generate will just start calling make big fraction, which will generate a new random number every time, new random fraction every time. And if you don't do anything to the contrary, it'll just go on forever. So generate is an example of a stream operation that generates an infinite size stream. If you think about most of what we've looked at so far, things where we take collections like a list or a hash map or whatever, those are fixed size, so they're bounded. In contrast, generate generates an infinite stream. There's other infinite generator methods like iterate as well. And so obviously we don't want to run forever, so what we're going to do is we're going to say generate new big fractions up to this number, which is S max fractions, which might be 10 or 1,000 or 1,000,000 or whatever you want, right? Some number. And so what this will do is this will make sure that we only generate n of these things. But this is just a real clever way of generating n of something using streams. We then go ahead and call map. Now think about what's happening here. We've got, n big fractions, and we call map. And what that will do is that will call reduce and multiply fractions on every element. So every unreduced fraction that was generated up to the limit will then be called via the map aggregate operation, that intermediate operation called map, will then call this lambda function, reduce and multiply fraction, which will then go ahead and asynchronously do the reduction and do the multiplication. Right? So all that stuff is kind of chugging away, chugging away, chugging away. And then we compose the results, so we end up with a completable future to this whole thing. Okay. So that will then, of course, end up with completable futures to the big fraction results that were multiplied, right? Well, what we're going to do now is we're going to collect all of those functions, all of those completable futures. We're going to collect them all together, and we're going to return basically a single future to a list of big fractions that are in the process of being reduced. So this is a really interesting method, and we'll take a look at the implementation here in just a second of this thing called a futures collector. So remember, collect is a terminal operation, and its job is to basically gather, combine all the results for things that are running from the intermediate operations that come before it, which in this case is basically going to be a stream of of these reduce and multiply functions, right? So those things are all chugging away. And so what collect is going to do, we're going to get back a single completable future to a list of completable futures, an array of completable futures, whatever, you know, some collection of completable futures, all of which are in the process of being reduced and multiplied. But we only get one future back. And of course, the way this works is when all the other completable futures complete, the single future returned from collect will complete, but only when they all complete. So you can think of this as basically a, I guess it's actually, is it a demultiplexer? I always get this backwards. Multiplexer, demultiplexer. It's waiting for multiple things, and there'll be one output. So I guess that's a multiplexer, right? So this is basically a multiplexer that's going to get back one future. And then when that future is complete, in other words, when all the computations are done, what we're going to do then is we're going to go ahead and print the results, right? So then except will only get called back when this future completes. And that future will only complete when all of the other futures complete, all of which are running asynchronously, by the way. And we then go ahead and accept that result, and we call this callback consumer lambda, which, as we just showed a couple slides ago, is going to take the list and sort it with two different sort routines, and then pick the one that comes back first. And that's what will be displayed. Okay. Any questions about that? Yeah. Peyton. Oh, yeah. Oh, great question. Very good question. So I mentioned this before, but it went by so fast, I'm sure no one will remember it. If we were to say, you know, generate dot parallel dot limit, or generate dot limit dot parallel, or actually you can put it all the way up to the very end. You could say, you know, generate dot limit dot map dot parallel dot collect. As long as the word, as long as the stream operation dot parallel, or parallel, so dot parallel is how you call it. As long as parallel appears somewhere before we hit the terminal operation, then that whole thing will run in parallel. Now, it turns out you could do that, but you probably wouldn't want to. And the reason for that is that parallel and limit don't play together very well. And so you end up with a lot of extra overhead that you probably don't want. So this is already running all these things in parallel anyway. So having a parallel stream is probably overkill. In fact, it might actually run slower. So you probably wouldn't want to do that. All right, so this is super cool. And it also shows a couple other things. In addition to just making the program nice and tidy and concise, it also demonstrates how you can combine completable future related stuff, right? So things like our good friend reduce and multiply fraction, this guy. It shows how you can combine that with streams. So we can have completable futures used in the context of streams. And you'll need to know how to do that for assignment 3A and 3B. It's really, really cool. It also shows the ability to collect together a bunch of completable futures into one completable future to wait for that. That's what we often call sort of reactive model. You only end up with one point. You have to wait for everything else to finish, which is really cool. And it also shows how you can have a terminal operation in a stream followed by another operation that's just fluently chained onto it, which in this case is just going to be used to wait for, not wait is the wrong word, it's going to be called after this thing completes, right? So then except will be called after that thing completes. So it really demonstrates composition. Now the other way to think about this, well I'll talk about that. A good way to think about streams, about completable futures, is look at the right-hand side and just sort of get the flow. So this basically says, you know, reduce this thing and then multiply it, right? If you just look at the right-hand side, that kind of gives you the behavior that's being run, the actions that are being called. And then you look at the left-hand part, which are the names of the completable future methods, the completion stage methods or factory methods, to see sort of how it's being done. But, you know, you can almost, it's not quite correct to think of this as just running sequentially, because it's not running sequentially, it's running asynchronously. But that's sort of the logical flow in which things are happening, unless you have stuff like, you know, except either. Okay, so that's basically that example. That example should hopefully help you start to ferret out what you need to do for assignment 3A. Let's talk about runtime exceptions. So this is another feature that you need to be aware of. Basically, what these things do is they let you handle exceptions that may occur during the completion stages. And I'll talk about all three, and I'll show you two examples. So there are three methods that handle exceptions. One is called when complete, which is kind of a weird method because it really doesn't do anything other than just give you a hook to take some action if something completes successfully or not. It doesn't transform anything. Then there's handle and exceptionally. These can actually be used to transform the result in one way or another. So let's take a look at an example. So if you look at the actual code that goes along with this, you'll see that I have it set up to conditionally make the denominator be 0 or not. So sometimes when the denominator is 0, this will blow up because we're going to be dividing something. It's going to blow up in a certain way. So what we're going to do here is, if we end up, if you have a denominator of 0, an exception is thrown by the creation of the big fraction, because you're not supposed to have a fraction who's got a denominator of 0, right? That's bad. So an exception can be thrown in the context of this asynchronous call. And if that happens, then the handle method will have the result, this is the result, fraction be equal to null because it threw an exception, so it didn't actually get a real value. There is no fraction. If you want, you could find out what exception was actually thrown by getting the value out of this. So what we do here is, if there was an exception thrown, we're just going to return 0. We could throw an exception also, but we're just going to return 0. We're going to swallow the exception and return a 0. Otherwise, we're going to multiply the fraction that we got back from here by this constant. And then when we're done, we'll print the result out. So that's handle. Handle gives you a chance to differentiate between the normal case and the error case. Yeah? You really don't want to have null results. That would be bad. So if an exception is thrown, then the fraction will just be set to null. That's how you know it was an exception was thrown. Yeah. Yes. Here's exceptionally. This is one that's just meant to handle exceptions, right? This one will handle either exceptions or non-exceptions, right? You can handle both of them. It should have been like handle both. This just handles exceptions. So what you can see here is if we end up with, if an exception is not thrown, then apply will go ahead and do the multiplication, and exceptionally will be skipped. If an exception is thrown, then apply will be skipped, and exceptionally will be called, and in this case, we just return 0, right? We could have done something else. EX is the actual exception that occurred. If you actually run the program, it does a little bit more. I didn't want to put it all on the slide, but it does more stuff. And so that converts an exception to a 0 result. So that's basically just a way to handle exceptions and do something to transform the results in one way or another. Okay, so that's the end of this set of slides.